Yeah, great. So hi, I'm audible, right?
Yes, ma'am.
Yes, ma'am.
Great. I think we can start. So the recording is also there. Sorry for that. I have to figure out these things soon. Yeah, great. So good that you guys attended today's live session. We can discuss on the week 4 content for today's live session. So is my screen visible?
Yes, ma'am.
Great, great. So yeah, last session we were in hurry, but I think we finished the content that we are supposed to discuss during last week. But anyways, I'll pause for a while, and if you have any doubts regarding the content in these three parts, manipulation of the periodic signals or power or energy, if you have any questions related to these three topics, we can discuss for some time. Do you have any questions in these topics? I would just do a quick recap on these things. So the first thing that we discussed in our last class was about the periodic signals. So if you recollect the definition, so we call a signal to be periodic if x of t is equal to x of t plus some t prime for some t prime. If that happens for some t prime, then we call such a signal to be periodic. And if at all a signal is periodic, for periodic signals, if you remember, we have three different things. One is the fundamental period, fundamental frequency, and the fundamental angular frequency. And what is the fundamental period? Fundamental period is nothing but the minimum t prime for which x of t plus t prime is equal to x of t. So this fundamental period, we usually represent it by t naught, or we also use this capital T notation to represent the fundamental period. And the fundamental frequency is nothing but 1 by this T naught. F naught is 1 by T naught. And the fundamental angular frequency is nothing but 2 pi F naught. And if at all there exists no T prime, such that, in the entire real number line, there is no T prime, such that x of t plus t prime is not equal to x of t for any t prime, then we call such a signal to be not periodic signal, or we also represent it by aperiodicity, a periodic signal. Okay, so that is with respect to the periodic and periodicity, periodic signals and the periodicity. And we have seen couple of examples. One example is the summation of the rectangular signals, summation of the delayed rectangular signals. We saw that this particular example is a periodic signal, and we also saw how exactly like this particular signal is periodic signal, and the periodicity of the signal depends actually on the capital T value. So in this particular example, we took capital T to be 2, and we have seen that this signal is periodic signal with a fundamental period of 2. And we have also seen sine omega naught T signal. We saw how it is periodic, and we have also derived the fundamental. So if at all the signal given to you is sine omega naught T, or in other words, the other representation of the signal is sine 2 pi f naught T. So if you consider this signal, this particular signal, then for this particular signal, we have derived the fundamental period to be 1 by f naught. Okay, that is something that we saw, like what is the period of this particular signal. And we have also made a comment that the period of a periodic signal is nothing but so in a periodic signal, there is a constant repeating signal that keeps repeating at different intervals of time. So that signal, whatever keeps repeating, the period of that constant signal is nothing but the fundamental period of the signal. We made that comment, we saw that. And we have also seen certain examples, sine 7 pi t. Suppose if you are given the signal and if you are asked to find the period of this particular signal from the above example, we saw if you have a form sine omega naught t, then the period of that particular signal is 1 by f naught. And you can write the sine 7 pi t in sine 2 pi f naught t form, from which f naught is nothing but 7 by 2, and hence the fundamental period is nothing but 1 by f naught, which is 2 by 7. Okay, so that is something that we saw. And even for the cos omega naught t signal, the fundamental period is 1 by f naught. And there are two comments we made again, like we revised these comments from professor's lectures. So the first one is time shifting will not affect the period of the signal. Suppose if you shift the periodic signal, then the fundamental period will not get affected. But if you time scale a periodic signal, it affects the fundamental period of the signal. And for the scaled version of the signal, the fundamental period is t by mod a. Okay, this is also something we have seen, right? And suppose, and also we have saw the period for the manipulated signals. That is, suppose if you have x1 of t, which has a period t1, and x2 of t, which has a period t2, then x1 of t plus x2 of t, or x1 of t multiplied by x2 of t is the signal periodic. That is the first question to ask. And to answer that question, how do we do? So we evaluate the fundamental periods t1 and t2 of the signals, and then we evaluate the fraction of this t1 and t2, which is t1 by t2. Am I audible? Hello?
Yes, ma'am.
Great. Just let me know if I'm not audible, okay?
Sometimes it's going like wave, ma'am.
It's like, yeah, because it's breezy. I need to sit somewhere outside to get the signal, and it's breezy over here. But is it
Oh.
too disturbing to you guys?
No.
Right?
Now it's fine.
All right. Okay. So you first have to evaluate this fraction. If at all the fraction turns out to be a rational number, then we say the manipulated signal, be it x1 of t plus x2 of t, or x1 of t multiplied by x2 of t, that is periodic. We also saw the cases. Why is this? Just 1 second. Yeah. So we also saw this cases, the other two cases, x1 of t minus x2 of t and x1 of t divided by x2
Ma'am,
of t.
a screen is not visible.
Oh, sorry. Let me share it again. Oh, right from the beginning or only just now? Hello?
Just now.
Only
Just
just
now.
now.
Okay, right. Okay. So, yeah, once you evaluate the fraction, like if the fraction turns out to be the rational number, then we say the manipulated signals are periodic, or otherwise they are not periodic. We have also seen the other two cases, x1 of t minus x2 of t and x1 of t divided by x2 of t can be written in this form. So x1 of t minus x2 of t can be written as x1 of t plus minus x2 of t, and x1 of t divided by x2 of t can be written as x1 of t times 1 by x2 of t. Hence we are not bothered about the other two operations, so we only think about the plus and multiplication here. Okay, so if t1 by t2 is a rational number, if it turns out to be a rational number, then we say the manipulated signal is periodic. Okay, and what is the period of the manipulated signal? The way you calculate t is either you take the LCM of these two numbers t1 and t2, or the simplest way is take this fraction. T1 by t2 is m by n, and from this you get nt1 is equal to mt2, and your fundamental period of the manipulated signal will either be nt1 or mt2. Okay, and this is what we have seen, and we have also seen one example, nice example. So we took sine t plus cos pi t. So what is this? The first question to ask, is this signal periodic? To answer that, we evaluated the fundamental period of the first signal, which is sine t, x1 of t, And the fundamental period of that signal turns out to be 2 pi. And for the x2 of t, the fundamental period turned out to be 2. And when you found the fraction t1 by t2, it is 2 pi by 2, which is equal to pi, which is not a rational number. Hence, this summation is not a periodic signal. Okay. And we have also seen another example, the sum sine t plus cos 2t. And the fundamental period of the first signal is 2 pi, and the fundamental period of the second signal is pi. And when you evaluate the fraction t1 by t2, it turns out to be a rational number. Hence, the signal is periodic. And the fundamental period is from this fraction, you see t1 is equal to 2t2. Hence, the fundamental period is either t1 or 2t2, which is nothing but t1 is 2 pi. So, the fundamental period would be either 2 pi or 2 times t2, which is also 2 pi. So, the fundamental period is 2 pi. Okay. So, this is all we have seen in the last class. I don't know why my pencil seems to be not working. It doesn't work. I don't know how to write the topics. Okay, let's see. Right. And the other things that we have seen. Let's see if it is charged. Okay, so the other parts that we have seen are, one is the energy. The energy of the signal is defined as minus infinity to infinity mod of x of t whole square dt. And the power of a signal is defined as limit t tending to infinity 1 over t integral minus t by 2 to t by 2 mod x of tau whole square d tau. So the power is nothing but the average energy concentrated in a particular time frame t. So that is known as the power of the signal. Okay. So how do you calculate energy and power for any given signal? You evaluate these two terms and you evaluate the energy and power. Okay. So that is something that we have discussed. And suppose if any two signals x1 of t and x2 of t are orthogonal, then the energy of their sum is nothing but, usually the energy of the sum is not the energy of the individual signals. It's not the sum of energies of the individual signals. That is not true usually. But if at all the given signals are orthogonal, then the energy is nothing but the sum of their individual energies. Okay, this is also something we have seen in the last lecture. And all finite energy signals in place for which the energy is finite, for all, so suppose if at all you are given a signal and if you evaluate the energy, if that energy is a finite number, then for such signals the power is 0. You don't even need to evaluate. So all finite energy signals are 0 power signals. Okay. Likewise, if at all you evaluate for any signal power, and if the power turns out to be greater than 0, for all such signals you don't even need to evaluate energy. They are 0 energy signals. Okay. And if the power is a finite term for any signal, for such signals energy is 0, and such signals are called power signals. Okay, or 0 energy signals. And if at all for any signal energy is finite, then the power is 0. So such signals are called either energy signals or 0 power signals. Okay, so this is something I would like you guys to remember. I have no idea why nothing works in today's class, but let me figure it out. This will not work from my iPad. Let me figure out a way to do today's class. Okay. Right. So these are certain things that we discussed, and the other parts are if at all x of t has energy Ex, then x of at plus b has an energy Ex by mod A. That's a nice calculation which you can do as an exercise. So what you have to do is, for the x of at plus b signal, go back to the formula of the energy signal, plug in x of at plus b dt mod square, and try to evaluate that expression. What you would get is that expression would turn out to be this whole integration divided by mod A. Okay, hence the energy of x of at plus b is nothing but Ex by mod A. But note this point for the power signals. So for power signals where the power is a finite quantity, if at all x of t has a power of px, then x of at plus b will not affect the power of the signal. The power remains the same. Okay, this is something that you guys may want to remember. And yeah, so this is something that we discussed in the last lecture. Apart from this week 4 content, it's the summary of all these things, summary of what we have done in week 1, week 2, week 3. Other than that, there is a concept on delta signals. Okay, so my iPad pencil seems to be not working for some reason. I have no idea why it's not working, but we can do today's class in some way. I would help you guys if you can, if you guys cooperate. I'll orally tell you on the delta signals. We can go slow. You guys can write it down on your notebook. If you have any questions, you may ask, or I'll try to use webboard. What say webboard and maybe. This is not what I want. Alright, maybe I'll. Great. Okay. This is there. I can write it. Okay. Okay. So, sorry, I have to type with my hand. So, give me some time. So, it's week 4. Please,
Ma'am,
excuse me for today. Yeah.
this idea may be vague, but if you dictate, can I write?
Yeah, that's what I thought. I'll dictate. Maybe you guys can keep
No, no,
writing,
no.
but then.
I have a writing tablet. If required, I can write.
Oh, maybe not required. I'll figure out something. Yeah.
Okay.
So it's only on delta signals. There is no new topic apart from the delta signals. Satyam, I got to see your question on email. I can help you after this class session is over. Okay, I can help you with that question. You emailed me something. I got to see that just now. We can discuss on it once this class is done. If you still have doubt on it, okay. So delta
Okay, ma'am.
signals delta signals are like very nice signals to work with. They are very easy. The only thing you have to remember for delta signals is the area of a delta signal. If you evaluate on any time, any particular time, the area of the delta signals is always 1. And how do you represent such signals? So such signals, delta signals, are represented as you have, on your time axis, you have a straight line, okay, and when you evaluate the area of this signal across the time axis, it takes a value of 1. So this is the representation of the delta signal. Okay, so this is known as delta of t, where this is t. Okay, so this is all it is with the delta signal. So delta signals are some signals when you evaluate the area across the entire time axis, the area. So how do you evaluate the area? You sum it over all the values on the time axis, and the time axis can take values from minus infinity to infinity. And when you evaluate the area of that signal minus infinity to infinity delta of t dt, that area turns out to be 1. So this is all with the delta signal. Such signal is called a delta signal, okay, unit delta signal, because its area is 1. And the properties, there are like important properties for this delta signal. If you can learn these properties, I think any problem on delta signal you will be able to solve. This is, again I'll repeat, this is very very important signal. Anywhere you go in electronic communications, you can't avoid the signal. That is why the signal is treated separately in week 4 with more focus on it. uh, uh, I mean, professor could have introduced the signal in the earlier lectures itself. Because this is an important signal, it was treated in the later weeks, okay? So try to have some more focus on this particular signal. And the properties are this. The first property is integral minus infinity to infinity delta of at plus b dt is just 1 by mod a. Okay, so you guys can prove this out. I can help you with the proof just now. I don't have a pencil to write it up, but I can help you with the proof. The proof goes as follows. Okay, if you guys have a notebook with you, I'll dictate. Maybe you can start trying to do the proof for this part. Okay, so let's take a particular example first. So let's take a to be a negative number. Okay, so which is delta, which is of the form, if you take a to be negative number, that will be of the form minus a plus b dt, right? So this is when a less than 0, and you want to evaluate minus infinity to infinity. Now what you're supposed to do is, let this entire minus at plus b be some t prime. Okay, so call this to be some t prime. When you call this to be some t prime, what happens to dt prime? Dt prime is nothing but minus a times dt, right? And what happens to the integral limits when t is minus infinity? T minus infinity implies t prime is plus infinity. And when t is plus infinity implies t prime is minus infinity, right? So these are the cases. And what happens to this particular integration? So this becomes integral infinity to minus infinity del of t prime times minus a times dt prime, correct? And this, so when you interchange the limits on the integration, so this is infinity to minus infinity, when you ulta the limits, it becomes minus. So this is, this minus and this minus gets cancelled, and it would be just integral minus infinity to infinity del of t prime times, sorry, this is dt prime by a. This is by a. This is by minus a, dt prime by minus a, right? So this is what you will be left with. When you call this particular element to be some t prime, and when you try to evaluate this, and when you interchange the limits accordingly, this is what you get. And 1 by a is a constant which can be taken outside. So this is 1 by a times integral minus infinity to infinity dt del of t prime times dt prime, and area under a delta function is again 1. So which will give you 1 by a, right? Any questions with this? You guys try to work it out. And if you have any questions, I will help you. Like, if at all with any part. At least in this. When a less than 0. I have no idea what happened to my pencil. Didn't expect this. Sorry, guys. I was expecting my... I mean, I never expected that my pencil will break down at some point. Any questions in this? Hello?
No, ma'am. It's fine.
No, right? So
Yeah.
similarly, when a is greater than 0, you can see that this particular so even when a is less than 0, you can see that this particular integration will be mapped to what? 1 over a integral minus infinity to infinity del of t prime dt prime, and this part is 1, so it is 1 by a. So even when a is negative, it is 1 by a. Even when a is positive, it is 1 by a. Hence, del of integral minus infinity to infinity del of at plus b dt is nothing but 1 by mod a. This is the first important thing for you guys to remember. So this is one property of the delta function, very important. No, the first thing is to remember the definition. So definition of the delta function itself is an important. The area of the delta function across the time axis is always 1. And the second property is when you time scale the delta function, the scaling will not, the shifting will not affect, but the scaling do affect the area under the delta function. And this is what it is. And from this, you can calculate several examples. Suppose if you are given something like what? So suppose if you're given integral minus infinity to infinity del of 3 minus t dt, what happens to this? Can someone help me? What is the answer for this? Are you guys with me?
-1.
Minus 1. How? Isn't this 1? If you guys just use the above thing that I have told you, where integral minus infinity to infinity del of at plus b dt is nothing but 1 by mod a. So here what is our a? Our a is -1 and b is 3. And what is 1 by mod a? 1 by mod -1, which is 1, right? Yeah?
Yes, ma'am.
Right. Okay, so this is how you can go with it. And so yeah, this is one nice interesting
When you're
problem.
in this, I have one doubt in lecture.
Mm.
He worked out one thing, the my between minus infinity to t del f.
Mm.
So in that he says that integral minus epsilon to epsilon is 1. So why would he take minus epsilon? 0 to
Even,
epsilon itself is 1, no?
0 to epsilon is not, no, delta function is defined at 0. So when you take 0 to epsilon, it's not a valid signal. So delta function is symmetric. So the area of the delta function is 1, but it is symmetric across the both, it's symmetric across the 0 axis. So the integral of minus epsilon to epsilon of the delta function. So the area, so this area is concentrated across 0. That is the point, you may have to remember. Okay. So it's not, so suppose if you define del of some, let's say, sorry, let's not go to that. So yeah, delta function is concentrated around 0. So that is something you may have to remember. So for a very small epsilon, so it is concentrated, the area should be 1. So area should be 1 in place when it is, when it is between minus epsilon to epsilon. It may take the value, what? How can you make that? So it may take a value of 1 by 2 epsilon, right? So because only then the area you can make it to be 1, right? Am I talking correct? Yeah. So if it is concentrated between a very small interval, you could see what value it can take. But like you are evaluating across the large interval, The only idea that you would want to make is the area of the delta signal across the time axis is always 1. Okay.
Okay.
So that is something you may have to, yeah.
So that means we should not say 0 to epsilon at all.
No, 0. It is concentrated around 0. The area is concentrated symmetrically around 0. Okay. So that is something you may have to remember. Okay.
Okay.
Right. So yeah. All right. So this is an interesting property. I hope everybody is okay with this property. If you guys are okay with this, let's go to the next property of the delta signal. That is all you need with the delta signals. The area around the area of the delta signal across the time axis is 1, and when you integrate and you time scale and shift accordingly, the area varies likewise. So time scaling does affect the area of the delta signal. Okay. And the other interesting property is, suppose if you take x of t, some signal x of t, and if you multiply this delta signal, a shifted delta signal, this is always equal to x of t naught multiplied by x of t minus t naught. Okay, this is another nice interesting property. So if you remember this property of the delta signal, that itself is sufficient to solve any problems on delta signals. If you want, I can explain you a particular problem that I have given you guys in your practice example. So this is all it is. So these are the 3 important properties of the delta signal. One is the area one, and the second one is time scaling and shifting. Shifting will not affect, scaling does divide the delta signal by mod A, the area by mod A. And when you multiply some signal x of t by a delayed version, del of t minus t naught, and the delay is t naught. So this is equal to the signal taking the value at t naught times the original delta function, the delayed delta function. Okay. So this is very nice property. Don't get confused. X of t multiplied by del of t minus t naught is the signal value at this particular t naught times this function. Because if you see intuitively, the delta function takes this value around some particular value, either at 0. If it is a delayed version, it is symmetrically taking values around t naught, right? And when you multiply this with the original signal, all other way, like all at all other values on the time axis, the signal is 0. So it is concentrated only across either at 0 or t naught. When you multiply the signal with x of t, the multiplication should give you something around this point, x of t naught times this delta function, right? So intuitively it makes some sense, right? When you multiply these two signals, it should be x of t naught times this delta function. So that is what this property is telling. When you multiply the signal, any big signal you take, x of t could be any big signal, it can run across even infinite time. When you multiply that signal with this delta function, delayed delta function, so that would be the signal taking the value at particular t naught times del of t minus t naught. Okay, to help you guys, I'll solve one little example from what I have given in your practice assignment, so that this idea is very clear in your minds. Let me pick up one example. Okay.
Ma'am,
Yeah.
we still haven't come till practice assignment.
No,
Maybe
I'll just pick up one example from the practice assignment, and I'll show how you can utilize this property.
yeah.
That's what.
So if you can pick up some other example, then it will be nice, ma'am. Because we will solve ourselves when we come to practice assignment. We want to solve it ourselves first.
All right. So, okay, let me formulate some example then. So what could be the, so okay, take this signal. Okay. So integral minus infinity to infinity some cos 2 pi t, okay, evaluate cos 2 pi t times del of t minus 1 dt. Can someone tell me what happens to this? So let me solve this particular example. So let me call this to be my x of t, and this is in the form x of t times del of t minus 1. What happens to x of t? So this is my t naught. So what happens to x of t times del of t minus t naught? That is simply x of t naught times the same del of t minus t naught, right? Integration remains the same, right? And what is your x of t naught, which is cos 2 pi t naught? T naught is 1. So cos 2 pi t naught is cos 2 pi. What is cos 2 pi? You guys should be interactive. What is cos 2 pi?
1.
-1.
1.
Cos 2 pi is 1. So this is nothing but minus infinity to infinity 1 times del of t minus 1 dt. And what is this now?
1.
What is, yeah, this is 1, right? So that is how you can utilize that above property. Or at times people might give some confusing expression, like, you know, I myself will try to confuse you guys with some big expressions with such properties, but everything breaks down so simple once you learn that property. So suppose if you have minus infinity to infinity e power minus 10 times t times del of some 7/2 minus 8.5 t dt. Okay. Now, can someone tell what happens to this? Yeah, this is confusing, right? So when you have such things, what you have to do is what you know the property. So try to first write down the property. So you know x of t times del of t minus t naught is x of t naught times del of t minus t naught. This is the property that you know. But the given delta function is not in this nicer form. It is not in t minus t naught form. Now what you have to do, have to get it somehow in t minus t naught form. How can you get it? Call this expression some t prime. Okay. When you call that t prime, what happens to it now? So t prime is 7/2 minus 8.5 t, right? And so I want to get rid of this 8.5 t. What can I do? So instead of calling this entire thing t prime, let me call 8.5 t minus 8.5 t alone. I'll call some t prime. Okay, or 8.5 t, or okay, minus 8.5 t, let me call t prime. So t prime is my minus 8.5 t. And what is dt prime from this? dt prime dt minus dt prime by 8.5 is dt. And the limits would be minus infinity becomes infinity, and infinity becomes minus infinity, right? So the limits would be infinity to minus infinity. So when you interchange the limit, that minus and this minus gets cancelled. And what happens to the original expression now? When you see the original expression, so what happens to this is this now you can write as integral minus infinity to infinity e power minus 10 what is your t? T is t prime by minus 8.5. So this is t prime divided by minus 8.5, right? Times del of 7 by 2 plus t prime times dt prime divided by 8.5. Is that okay?
Yes, ma'am.
This is all right, no? So now from here, you know how to evaluate, right? From this, how do you evaluate? Your T naught is now what? Minus 7 by 2, right? Because T, what we have seen is T minus, del of T minus T naught form. So your T naught is minus 7 by 2. And this would be e power minus 10, sorry, plus 10 by 8.5, which is 100 by 85 times 7 by 2 times del of t prime plus 7 by 2 times dt prime. Here 1 by 8.5 is also there, that factor, which is minus infinity to infinity. And this part is now a constant. And you can get it out of the integration, and the area will not be affected under time shifting. So that would be 1. So the final answer would be this highlighted part. Is that clear? Yeah?
Yes, ma'am. Yes, ma'am.
Yeah, so that is all it is with the delta functions. I think in week 4, the important topic, apart from whatever was discussed in the previous weeks, is this particular part. And I think I gave you guys a nice clarity on the delta functions. So these are the 3 important properties to remember for delta functions. Area is 1, time shifting will not affect, scaling does affect the area, and x of t times del of t minus t naught is x of t naught times del of t minus t naught. When you are given with a complicated expression like this, don't get scared, but instead try to write it down in the form that you already know. Okay, when you try to break it down, I think finally you get some nicer expression. Even though it looks complicated, you can solve it well. Okay, so these are the things I wanted to discuss in today's live session. Other than this, I don't have anything else to discuss for today. But if you guys have any specific doubts regarding the lectures or anything, I'm here for another 10 to 15 minutes. Yeah. I'm sorry, I planned to discuss so many things today, but then my pencil stopped working. But I think I covered the content. So there's no extra thing other than this. Yeah. So if you guys have any specific questions, please feel free to ask. We can discuss on those questions for the next few minutes.
Ma'am, can you just scroll up to the previous problem with the cos problem?
Yeah.
Okay.
Yeah. Quiz is coming up. So I think Saturday's live session is going to be crucial. So please plan to attend. I sent the final quiz paper to the team. Yeah, so if you guys understand the lectures, if you guys do the practice assignments, and if you guys have attended the live sessions, understood, the concepts correctly, you guys can do well in the quiz. So don't need to worry about that. But yeah, so 4 weeks content will be tested in the quiz. I don't know if I'm allowed to give the format of the question paper or anything. Usually we do that at the institute. Since I don't know, I'm not going to touch that part. I don't know if I'm allowed to tell, how the format of the question paper would be. That I don't know. So it'll be mostly multiple answer questions. It will be in the level of your assignments. So you may not need to worry if you listen through the classes and solve your assignments, clarify all your doubts. I think you guys will do well. Okay. So just go through the summary notes, whatever we discussed. It's always good to remember the summary points. So just to revise, the topics would be time shifting, scaling. You guys should be familiar with how to shift from x of t to how to delay a signal, advance a signal, scale a signal, scaling in the sense compress, expand. And if you're given a scaled or shifted version of the signal, how to go back. There are certain steps we already visited, right? So make sure you guys are comfortable enough with doing those things from x of t to x of at plus b, and from x of at plus b to x of t. Make sure you guys know those steps. So just to give you just to go back to the memory. So from x of t to x of at plus b, we first scale, we first shift by b and then scale by a, right? And to go back from x of at plus b to x of t, we first do a shift of minus b by a and then scale by 1 by a. Right, so those steps, please go back with whatever we discussed in the previous live sessions, and try to make some summary points and try to remember such things. So shifting, scaling will be there, and what else? Periodic signals, periodicity, and the properties of the signals. For real signals, we have even signal, odd signal, even symmetry, odd symmetry. If you're given some signal which has both even and odd parts, how do you find the even parts and odd parts of the signal, right? So the even part would be x of t plus x of minus t by 2, and the odd part would be x of t minus x of minus t by 2. So you guys should be familiar with plotting such things, and also the symmetries, conjugate symmetry. What is conjugate symmetry? If x of t is equal to x star of minus t, then we call such symmetry as the conjugate symmetry, which is defined for the complex conjugate signals. And we also know, so a complex conjugate signal can be, a complex conjugate signal will have two parts. So x of t can be written as the real part xr of t plus j times the imaginary part. And we also saw when the given signal is conjugate symmetric, we know what happens to this real part. So the real signal is even, and also the imaginary signal is even when the given signal is conjugate symmetric. If the given signal is conjugate asymmetric, we saw the real signal is even, but the imaginary signal is odd. These are certain things that we have seen in the earlier live sessions. So I hope I would advise you guys to go back and revise those things. So those are with respect to the properties of the signal. Once the properties of the signal are done, we have seen periodic signals, periods, a period, and the other analysis such as finding the energy of the signal and power of the signal, right? And then other than this, we have this delta things, right? So this is all we have: time shifting, scaling from both sides, from here to there to here. And then the properties of the signal: even symmetry, odd symmetry, conjugate asymmetric, periodic signals, aperiodic signals, fundamental period, fundamental frequency, and then energy, power, and this delta function. Okay, so make sure you're comfortable enough with all these topics. You guys will do well. I think the quiz is for 3 hours if I remember correctly. Okay, we can have a better discussion on this on Saturday. You guys can go through all these topics. If you have any specific questions to ask, come back to me on Saturday's live session. Okay, we can discuss that. Right?
Yes, ma'am.
Yeah. If you guys don't have any other questions, with your permission, I would like to end today's live session.
The quiz, every paper is for 3 hours. No, for 2 hours, right?
2 hours. I'm not sure. I saw somewhere it is for 180 minutes. So I don't know. I'm not sure. You guys should tell me. I'm new to this thing.
Oh, yeah, 180 minutes, right.
180 minutes is for final exam.
Okay, but for the quiz, it is for 2 hours, huh?
Yeah.
Okay.
Not even 2 hours. Subject only for 1 hour. 4 subjects together for 4 hours.
All right. Okay. అందుకే 2 years. Okay, yeah. So if you guys don't have any other questions, yeah, we can break today's live session. Satyam, please stay. I would like to clear your question.
Okay.
Yeah, this we can leave. We can end the session. Yeah.
Thank you, ma'am.
Yeah. Thank you. Thanks for attending.
Thank you.
Satyam, with regards to your question, so let me open and share your question on screen so that. Were you able to find answer on your own, or are you still having trouble with that question?
Ma'am, I got the answer, but in practice assignment it is showing wrong. It's shows
Which question it is? Could you remind me?
practice assignment 3 question 10, the last question. I got that the signal is conjugate symmetric, but it is shown that it is conjugate asymmetric.
No, that signal is conjugate asymmetric. So I'll tell you the steps. Can you write it down and tell me if you know if the steps are wrong? So could you try to evaluate first x star of t? Hello? Hello?
Yes, ma'am. Yes, ma'am.
So what is x star of t? X star of t is t e power minus j alpha t sine. Let me share my screen. So if I remember correctly, the given signal is this. So x of t is t e power j some alpha t sine omega naught t, correct?
Yes,
Hello.
ma'am.
Now what is x star of t? X star of t is t e power minus j alpha t sine omega naught t, correct?
Yes, ma'am.
Now what? Now what is x star of minus t? This is minus t e power j alpha t. Sine of minus t is sine t. So that is just sine omega naught t. Correct? Hello?
Ma'am, it's minus sin t, no?
Sine minus t is minus sine t or sine t?
I
Minus
think it's
sine t.
minus.
Oh, is it minus sine? Okay, okay. Then I think you may be correct. It may be conjugate symmetric. All right. I'll update the answer. Thanks for letting me know this. Yeah. Okay. I'll update that. I'll update the answer. So it is in the practice
Okay, ma'am.
assignment only, right?
Yes, ma'am.
Okay, I'll make an announcement on this. Yeah, it's conjugate symmetric then. True. Yeah. Thanks for letting me know, Satyan. Yeah, all right. Yeah, is that okay? Any more questions or
Yes,
can we
ma'am.
break? Can we break the session for today?
Yes, ma'am. Sure.
Yeah, yeah. Thanks, Subhash. Good night, guys. So I'm
No,
ending.
Thank
Yeah.
you, ma'am.
no YouTube. Sorry, no YouTube channel for this course. No?
For the live recordings, you mean?
Yeah, ma'am.
But the live recordings are being uploaded in some folder, right?
No, they are being updated on DS Electronics YouTube channel.
Are they updating it? I am not sure. I can
Yeah,
only
they are
give
updating
them
it.
this. Oh, they're updating it, right? So
Yeah.
then what is this YouTube channel? I don't know
No,
about it. So what?
usually all the other courses there will be separate YouTube channel for each course.
Oh, is that okay? I'll check with them. I'm not aware of this. I'll
Yeah.
check with them. Okay.
Usually other courses they will live stream, not record.
Oh, they will live stream. Okay, I'm not. I don't know those things, but I'll check with them. Yeah.
Okay, ma'am.
Yeah. Thank you. But this is okay, right? This is convenient only. You guys are
Yeah,
able
ma'am.
to access the videos, right?
Yeah.
Okay, great. Yeah. Thanks. Thank you both. Yeah. Bye.
Thank you, ma'am. Good night.
Good
Thank
night.
you.
Bye.